Okie dokie. Dropped a Disney bomb in the lounge to keep the littlest one away. You might hear the dulcet tones of Cinderella over the back of this video, for which I can only apologise. And she might come and join us. Who knows? Yeah. So this is an opportunity for us to go through the light independent stage. Now, remember from the two previous videos that we've done, one of the things to finish off in order to go through and summarise the light dependent reaction is, so LDR, light dependent reaction, LDS, light dependent stage, doesn't matter which way. I know you desperately want me to go through and say potato, potato. No, well, I'll say it, potato, tomato. So yeah, it doesn't really matter which one you go through and call it, but this one from the light dependent reaction going in and what's been coming out. Well, the whole point of this is that we are going to go and reduce a load of coenzyme NADPH, or you could call it reduced NADP. We're going to produce some ATP and we're going to produce some oxygen. Everything else, if you think of the the actual physical products that come from this reaction, they are part of the system, sort of an intermediary from one place to another, rather than a final product. So there is room for maneuver there, but this is what I think of it anyway. So what's going into it? Well, of course we've got water going in. Would you include light in this process? But it's not really physical. You can think of a light as being a photon, a particle of light, but it's rarely that you actually think of it as being a tangible reactant. Are you going to go through and include NADP that then needs to be reduced? Well, yeah, probably. Are you going to say, well, actually, if we're going to produce ATP, we need some ADP and some inorganic phosphate to be going in. Again, room for manoeuvre. Work with it as best you possibly can. I'll try and simplify it as best we can. Why do this? Well, it's a nice little recap of what we've been doing before. So in the previous video, there's the light dependent reaction, and there's also chemiosmosis as well. And then when we're focusing now on the light independent stage, you need to be, it really is the glue, the mortar that actually goes through and binds the whole process, process together. Yes, again, there's a chronology, a step-by-step reaction that will be occurring, but it is then inexplicably linked with the work we've been talking about previously. So, because it's a cycle, the Kelvin cycle or the light independent reaction, being a cycle, it goes round and round. You can start anywhere you like, really. I've always, historically, I don't know, it's just the way my brain works, but I always think of, right, so I've got RUBP, ribulose bisphosphate, and then at the top here, maybe brown. I know you're commenting on just how you liked the colours. We'll see how many colours I can throw at this one without making you physically sick. And up here we have the enzyme Rubisco. So the enzyme Rubisco, like enzymes, is the site of a reaction. So our RUBP is going to go into one of the active sites that we've got here. Now RUBP is a 5-carbon molecule, and also going into that is carbon dioxide. So CO2 is going to go into the top here. Obviously only one carbon in CO2. That's going to bind into that one. The enzyme will do its enzyme business and will catalyze the reaction, producing a 6-carbon molecule. And sometimes this is used within the. Sometimes this is shown within the cycle. Other times not. This is a very unstable molecule, for me personally, I've always got to have it as part of the Calvin cycle, as part of this cycle, because I'm going from a 5-carbon molecule to a 3-carbon molecule. A lot of diagrams will bypass this stage altogether and take you to the next bit. For me, in my mind, I've got to show this intermediary molecule, unstable as it is, will exist, but then that will go through and produce some GP, a 3-carbon molecule. So GP is going to be produced. Glycerate phosphate, you can glycerate 3-phosphate. You can reference it as GP. Very, very rarely would you be penalised for writing down RUBP and GP. You know, the summative version of their names. Not giving their full name doesn't really matter from my experience of exam questions, but familiarity with their full name is important. So instead of RUBP, you've got ribulose bis phosphate. Instead of GP, you've got glycerate 3-phosphate. Now that in turn is turned into TP. Drop the pen lid. TP or triose phosphate. Okay, so again, triose must be another 3-carbon molecule. Something is occurring, something is happening to this molecule to be turned into this molecule, because actually we've got, in order to turn GP into TP, there's 2 additions that we need to have. We've got to have NADPH, or NADP. NADPH will be converted into NADP, so we've got some hydrogenation happening here. We've got the addition of some some hydrogen here. And in order to go through and just muck around this molecule, to go through and change it from one form into another, also often requires some chemical energy, and that chemical energy will obviously come from the ATP molecule. And inorganic phosphate will be chucked out of that, but it's using some of that chemical energy in order to convert GP into TP. So this is where we are. So far, and then to convert TP into RUBP as this cycle continues, we're really going to have to smash up this molecule now, aren't we? Because we've got a 3-carbon molecule being converted into a 5-carbon molecule. Now that's going to require a huge amount of breaking of bonds and manipulation of these molecules itself. So what are we going to require in order to do this stage here? Again, another molecule of ATP will be required in order to smack around this molecule to convert it into RUBP. And that, in its entirety, is the Calvin cycle, or the light-independent stage. The thing is, so far, if you think of our photosynthesis equation, we've got water, we've got carbon dioxide going in now as well. So water went in from the light-dependent reaction, CO2 goes in in this light-independent reaction, and what have we got coming out? We've got oxygen coming out, but glucose is conspicuous by its absence in this situation. Where does it come from? Well, this is one of the things I'll go through and show you in just a second. But from the diagrams that I've always used, historically, there are different pathways for these intermediate molecules here, the GPs and the TPs, to go and take. So our GP, instead of actually being all converted into TP, can be converted into amino acids. And from those amino acids, we could go through and create a whole wealth of polypeptides. So amino acids, so GP could be converted, the molecules again would be smashed around all over the place in order to be converted into amino acids. Knowing the structure of a 3 glycerate 3-phosphate, what have you got to add to that to produce an amino acid? Well, an amine group. You've got to really check around these these molecules in order to get it. Once you've got the amino acids, then you can produce the polypeptides, the enzymes, the collagens, whatever it is that you want to actually go through and create. So that's one pathway it could go through and take. Another pathway that GP can take is to go through and produce some fatty acids. One constituent, apologies for the writing there, one constituent part of triglycerides, lipids, essentially. Well, again, still, we still haven't gone through and talked about anything to do with glucose. Now, for me, this comes off TP at the bottom here. From TP, there's an alternative pathway that it can take. Let me just move this up a smidge for you. The pathway that it can take, it can go through and form a hexose, a 6-carbon sugar. For example, glucose. Now, what could glucose be converted into? Well, glucose, if it was alpha glucose, could be used in order to make some amylose and some amylopectin, or commonly known as starch. So on this one here, I might sort of go, actually, I remember that's alpha glucose that's going to make that. Further detail I could add to this. I could include amylose and amylopectin here, but we'll keep it a little simpler. Or alternatively, if it's the beta glucose, yep, that's right, it could go off to form cellulose, required for cell wall formation, obviously any growth and repair that a plant might require. The alternatives that we've got here, so our sugars are glucose essentially. Well, that could also, we'll just sort of say glucose there. Oops, glucose. That 6-carbon molecule could just be turned into another monosaccharide. Could be turned into, with minimal beating up of that molecule, could be converted into fructose. Now, if we got some glucose and we got some fructose and added those, bound those together in order to form a disaccharide, we could create sucrose, linking us back beautifully to the stuff that we've done in year 12 and the biochemical molecules we've talked about too. The other alternative, obviously we've got fatty acids, got part of the equation to create some lipids over on the far side here, but the other route that TP can take would be to create a glycerol molecule, and then if we had, I better not muck up my formatting, if we had some fatty acids and perhaps 3 of those, let's say, and a glycerol molecule created, that would help us to create triglycerides or lipids. So when we say that plants are totally self-sufficient, well, yes, they are. I mean, they will make their own carbohydrates, they'll make their own amino acids, they'll make their own lipids, totally and utterly self-sufficient. The true autotrophs that we've gone through and discussed, previously. So one question that often comes up from students is say, well, what percentage of this GP will be converted into TP? How much of it will go that direction? How much of it will go this direction? Well, that links us into a very applied-based question that might come your way in the exams when they're asking you well, actually this plant is going through is producing a lot of this particular molecule. This molecule is a protein. what would you know would happen to TP production or IUBP production throughout it? Well, obviously, if the majority of GP is being steered down this pathway, dulcet tones of Lottie there. If it's been steered down this pathway here, then less would go for fatty acid production. For lipids, less would be converted into TP for all of these carbohydrate molecules that exist around the bottom, here. So that is our that's our cycle covered. The only other thing though that I think, the only thing that I would like to to talk you through, which is an awfully common question within the exams, is sort of linked into limiting factors, and often shown via a couple of graphs. Oh, just before I get there though, I'll show you this one here. From the exam questions that we've shared with you before, you've been presented with this question, and this question is another version of what we have beneath us here. How is this different? Well, it shows in this one here, it's a very simplified diagram, because we've got none of the NADPH or none of the ATP making an appearance here. But also, instead of actually two of the products, the amino acids and the fatty acids coming from GP, it seems that everything is coming from TP. We can roll with that. We can live with that, given this level of if you were left to your own devices and asked, well, where does amino acids come from? If you said GP, textbooks, revision guides, etc., etc., will have a very similar diagram to what we have here. The examinations, they're doing the typical examiner thing of just getting the knowledge that we think we've secured over the course of the years, and then tweaking with it to make us not so sure-footed. So but it's simplified, perhaps oversimplified in this in this particular situation. So don't worry, it's just examiners doing what examiners do best. And if they were to have it would be D, the amino acids coming from GP, and C coming from GP, as well as I've drawn on here. The fatty acid would be C in that situation. Doesn't really matter. We can, as you say, we can roll. We can roll with that. But as I've said there, one of the questions that often comes up is a graph question, asking you to go through and apply a bit of that mathematical prowess that you've got. So if you have time along here and a relative concentration, because I've got three things up on this diagram rather than just the one, and what the three things that will appear on these graphs will be IUBP, GP, and TP. So if we have time here, this is daytime, so lots of light, and this is nighttime, less light. How much GP would we have? Well, during the daytime, we'd actually have very little, not very much at all. And why? Well, because whatever GP is created is going to be immediately converted into TP, and then in turn into IUBP, because we've got a wealth of ATP and NADPH reduced coenzyme here from the light-dependent reaction. So from the light-dependent reaction, here's our products. It's going to be producing lots of NADPH, lots of ATP. Therefore, whatever GP is going to be created will then be immediately converted, because we've got a wealth of loads of these. We've got loads of those. That's going to be converted into TP. So GP, over the course of going into the nighttime, we would have less GP. And why? Well, because the light-dependent reaction will start slowing down, less ATP, less NADPH. This is not going to be converted into TP as quickly. Your TP in blue and RUBP will reflect purple. Doesn't matter, one is higher and one is lower. They'll have the opposite effect. A bright light, loads of TP, loads of RUBP. Why? Because it's being created from the GP that we're going to make. All of that GP, or a lot of it anyway, will be converted into TP and then into RUBP. So it'll be the opposite way around. So that's the day and night side of things. From this, it sort of does go through and say, well, the light independent reaction is often referred to as the dark reaction. Historically, I remember when I was taught, it was called the dark reaction, and that's actually the question that we have here. So the light dependent stage of photosynthesis referred to as the dark reaction. Why is that accurate and inaccurate? Well, it's a dark reaction because it doesn't require light. Okay, so that's an accurate side of things. Well, why is it inaccurate? Because for this cycle to be whizzing around, for the Calvin cycle to be whizzing around, we require the products of the light dependent reaction. So we do require light, but just in an indirect way. Okay, so getting your head around that side of the that very common question is important too. One more graph though, same as we've got before. So relative concentration, but in this time, rather than having day and night, we'll have lots of CO2 and only a little bit of CO2. Well, if you've got lots of CO2, then if you're lots of CO2, you're going to have lots of this reaction occurring, lots of GP, lots of TP will be produced. So where have we got that one? So PPP, so TP will be up here, and then that will go through and drop off, and our GP in pink. Show that one. Well, in this situation, why is RUBP going to be the opposite way around? If you've got loads of CO2, almost as we had before, loads of CO2, whatever RUBP is made is going to be quickly converted with the help of Rubisco and the addition of CO2. Lots of CO2, one would assume there's lots of Rubisco knocking around, but IBP is going to be created, then that's going to be quickly converted into GP and TP, keeping these levels, both of these levels high. So IBP would be quite a rare commodity in high CO2 conditions, because as soon as it's made, it's going to be converted into the other two. Convert that over, so into less CO2. These are going to be created, that's going to be created, GP into TP into RUBP, and then there's the bottleneck. So actually your RUBP concentration is going to go up and up and up and up and up. As CO2 levels drop, this is where the reaction starts to slow down, reliant on this CO2 limiting factor to keep the thing going. Would have a glut of RUBP left over. Or remaining, still in relatively high concentration within the plant itself. Okay, so the last thing for us to do is to think about our very basic foundations, our true summary. Well, what do we need for the light independent reaction? Well, we need CO2. What are going to be our products? Well, we're going to have glucose, we're going to have polypeptides, we're going to have lipids, and then and all of the starches, the celluloses could come from that as well. What else do we require for this cycle to keep on whizzing around? Well, we're not going to really go through and mention GP. We don't need GP because that's going to be created from wherever's there before. We don't need TP. We don't need RUBP because they're just encased within the cycle. What we do need is ATP and we need the reduced coenzyme NADPH in order to move the GPs into TPs, so that would be classed as the input that we have there. All right, so seamlessly, smushing everything together. The light independent reaction does tie up a couple of loose ends from the light independent reaction does tie up a few loose ends from the light dependent reaction in chemiosmosis for some. And as I've said there, I've got three videos now taking you through light dependent, light independent, and chemiosmosis. That should help you with your content. But remember, this is a huge topic, so a lot of application of this sort of content. So you need to be making sure that it is secure within those brains of yours. So it's a chronology. It's broken down to little bite-sized pieces. Make some notes, knock out some flashcards, whatever it is you're going to do, and then go through and hit the past papers as best you can. Any issues, please get hold of me. All right, take care. Oh my gosh, 26 minutes. Isn't that a bit long?